Hi students, and welcome to this lecture on continuity of functions. In a day-to-day life, we see many examples of events or things that are continuous in nature. Be it a railway track, a free-flowing river, the sound waves emitted from the horns of vehicles that enter our ears. These are all examples of continuous things or events. But things become discontinuous as well at some points. So in this lecture, we will talk about the continuity of functions and also see why functions become discontinuous at some points. So let's start this lecture. So first of all, let me ask you something. What does continuity in general mean? Continuity means that the state of being uninterrupted or the state of being continuous without any joints or breaks. Now we are talking about calculus, and the entire calculus is based on the concept of functions. So in this lecture we are going to study about continuity of a function. Now let us say that this is the graph of y equal to f of x. Now a is any point on the x-axis and the corresponding value of y would be f of a. Now let's take a point very much close to a but on the left side of it, that is, it is less than a, but actually it's very much close to a. Let us say that this is a minus h. The corresponding value of y would be f of a minus h. Similarly, if we take a point on the right side of a that is very much close to a but is actually greater than a. Let's take it as a plus h, where h tends to 0. Now the corresponding value of y would be f of a plus h. Now continuity of a function is defined as if the limit of fx when x tends to a negative, that is the left hand limit of fx at the point x equal to a, is equal to limit of fx when x tends to a positive, that is the right hand limit of fx at x equal to a is equal to f of a, that is the value of y at the point x equal to a. Then if this condition holds, fx is said to be a continuous function at x equal to a. Now let's come again to the meaning of continuity of functions in mathematics. If we say that a function is continuous at a point a comma f of a, then it means that there are no holes or gaps, or that it is unbroken at the point a comma f of a. So the same concept of continuity applies in mathematics, and the literal meaning is that if a function does not have any holes or gaps at any point a comma f of a, then the function is said to be continuous at the point x equal to a. Now if a function is not continuous at any point x equal to a, then it is said to be discontinuous at the point x equal to a. So the condition for any function to be continuous at a point x equal to a is that the left hand limit should be equal to the right hand limit, and which is equal to f of a. Once again, for a function to be continuous at any point x equal to a, the left hand limit is equal to the right hand limit is equal to f of a. Now let's take different cases when fx is discontinuous. Now case number 1 is if limit of fx when x tends to a negative is not equal to the limit of fx when x tends to a positive, that is the left hand limit is not equal to the right hand limit. And we know that when the left hand limit is not equal to the right hand limit, then the limit does not exist. So if we say that the limit does not exist at point x equal to a, then the function is surely discontinuous. The second case is if the left hand limit is equal to right hand limit but is not equal to f of a, that is the limit exists, both left hand and the right hand limit are equal, but these are not equal to the value of function at the point x equal to a. So in such case we say that the limit exists but is not equal to f of a. Now let's come to the case number 3, that is f of a is not defined. In such case as well, fx is a discontinuous function. Case number 4 is if one of the limit does not exist. So the different cases are if the left hand limit is not equal to right hand limit, then the function is discontinuous. If the left hand limit is equal to right hand limit but is not equal to f of a. The third is f of a is not defined, and if one of the limit does not exist. Now let's see these cases one by one. Case number 1 is left hand limit is not equal to the right hand limit. Now let's try to visualize it. This is the graph of y equal to fx. Now we see that the left hand limit is equal to L2 and the right hand limit is equal to L1. That is, if we approach the point A from the right hand side, then the value of the function is L1, and if we approach the point x from the left hand side, the value of the function becomes L2, and we see that L2 is not equal to L1. So in such case, we say that the limit does not exist, and so the function is discontinuous. So let's try to see an example. Discuss the continuity of fx equal to the greatest integer function of x plus 2 as x approaches 2. Now the given function is fx equal to the greatest integer function of x plus 2. Now if x is just less than 2, or we try to see the left hand limit, then when x is just less than 2, the value of greatest integer function of x would be equal to 1, and so fx is equal to 3. So when x lies between 1 and 2, then the value of fx would be 3, and when x is slightly greater than 2, then the value of greatest integer function of x would be equal to 2, and hence fx is equal to 4. So for the values of x which lie between 2 and 3, the value of fx would be equal to 4. Therefore we see that the left hand limit is equal to 3 and the right hand limit is equal to 4. Therefore the left hand limit is not equal to the right hand limit, and so the limit does not exist, and hence we can say that fx is discontinuous at the point x equal to 2. Now let's see case number 2, that is the left hand limit is equal to the right hand limit but is not equal to f of a. Now let's try to visualize it. This is the graph of y equal to fx. Now we see that if we approach x from the left side of a, then the value of fx approaches to L, and similarly if we approach a from the right hand side, then again the value approaches to L. Therefore the left hand limit is equal to the right hand limit and is equal to L. But the value of function at the point x equal to a is f of a, and which is less than L, or which could be greater than L but is not equal to L in such case. Therefore we say that the left hand limit is equal to the right hand limit but is not equal to f of a. Therefore the function is discontinuous at the point x equal to a. Now let's try to again see an example to understand this. Discuss the continuity of fx equal to x square plus 1 when x is greater than 2, 1 when x is equal to 2, and x plus 3 when x is less than 2. Now let's first try to calculate the left hand limit. So the function is x plus 3 when x is less than 2. Now let us say that x is equal to 2 minus h, and h tends to 0. So we put the value of x here in this expression and get the limit as equal to 5. Similarly, when we try to calculate the right hand limit, we put x equal to 2 plus h where h tends to 0. H is a positive quantity. So we see that the value of fx when x is greater than 2 is x square plus 1. So we put the value of x equal to plus h and get 2 plus h whole square plus 1, h tending to 0, and therefore the limit is equal to 5. Now we see that the left hand limit is equal to the right hand limit, but also given that fx is equal to 1 when x is equal to 2. So f of 2 is equal to 1, which is not equal to the left hand limit and the right hand limit. Therefore we can say that fx is discontinuous at the point x equal to 2. This is the value of function fx equal to x square plus 1 when x is greater than 2 is equal to x plus 3 when x is less than 2 and is equal to 1 when x is equal to 2. Now we clearly see that the right hand limit is equal to the left hand limit, but suddenly see that the value of f of 2 is equal to 1. Left hand limit is equal to the right hand limit but is not equal to f of a. Therefore fx is a discontinuous function at the point x equal to 2. Now let's look at case number 3. If f of a is undefined. So this is the graph of y equal to f of x. When x approaches a from the left hand side, then the value of function is equal to L. Similarly, when x approaches a from the right hand side, then again the value approaches to L, but the function is not defined at the point x equal to a. Therefore there is a break at this point x equal to a. Therefore we can say that the function is discontinuous. So once again we try to see an example. Discuss the continuity of fx equal to x square minus 4 divided by x minus 2 at x tending to 2. So we have to discuss the continuity of fx at the point x equal to 2. Now we clearly see that it is not defined at the point x equal to 2. So if we put the value of x equal to 2, this function fx becomes undefined. Now fx is equal to x minus 2 into x plus 2 divided by x minus 2. Now if I say that x is not equal to 2 but is close to 2, then we can cancel this factor x minus 2 and x minus 2 and we get fx equal to x plus 2. Now limit of fx when x tends to 2 is equal to 4. Therefore the left hand limit and the right hand limit is equal to 4. But we see that f of 2 is not defined. Therefore fx is a discontinuous function at x equal to 2. So this is the graph of x square minus 4 divided by x minus 2. At this case we see that the left hand limit is equal to 4 and the right hand limit is also equal to 4. But the function is not defined at the point x equal to 2. Thus fx is discontinuous at the point x equal to 2.